Hi. Almost done. I think there's 2 more videos to go. This one and the next one. I promise. So what's driving plate tectonics? Again, remember it's mantle convection. Touched on it a little bit in Unit 1, talked about it, sprinkled it in some of the sections of this unit, Unit 2. Let's just talk a little bit more about it. So again, mantle convection is that driving force of plate tectonics. Remember in Unit 1, I kind of likened it to like a lava lamp, how a lava lamp works. There's actually 2 possible models for convective heat. That's convection where the hot stuff rises, cold stuff sinks. So there's a couple of models. In one model, the entire Earth's mantle is involved in thermal convection. I'm kind of more on board with that. As a physicist as well as a geologist, it makes a little bit more sense to me. The second model, the convection cells, hot rising, cool sinking, is only restricted to the asthenosphere. That's that plastic, like really small part of the upper mantle just below the solid part of the mantle that's connected to the lithosphere. But in both models, spreading happens at the areas where the convection cell is rising, and then as it peels away from one another, that's where spreading occurs in both models, and trenches and subduction occurs where convection cells descend back into Earth in both models. So they have similarities there, it's just they go about it a little bit differently. So this is the entire mantle experiences convection, which I'm on board with that, all right? Just with, this is just me. With physics, how heat is transferred, it doesn't usually just stay nice and bundled up. I could be wrong, right? But heat from the inner core is transferred to the outer core. Heat from the outer core is transferred to the mantle. That mantle material is heated up. Hot mantle material rises. As it cools down, it sinks back down, and that's the convection cell. That's the convection cell, all right? In the second model, that only occurs in the asthenosphere, which is not by size this big. It's actually much smaller than that, but just for drawing references, that convection only happens in the plastic-like asthenosphere. I mean, and from that, the heat source is just the upper mantle itself. It doesn't really segregate like that, right? Heat transfers through all medium. To me, I'm on board with number 1 here. But in any case, they have similarities. So there's some sort of convection happening there, mantle convection. What it looks like, I guess can be debated. So in addition to the convection going on, there also might be some other things helping and aiding this movement that's helping drive plate tectonics, maybe moving things a little bit faster. One is called slab pull. So there's some diagrams here in just a moment, where slab pull is the slab is the cold and dense part that's being subducted is pulling the rest of the plate down with it. So because it's kind of getting pulled down, it's pulling the rest of the plate with it, helping to facilitate that movement. It's kind of like, in the movies where someone's dangling off a cliff and holding on to someone else and they're slowly falling down as well. That's kind of what I picture it as. Or maybe it's all working together, there's ridge push. So at these spreading centers, at divergent boundaries, for instance, these oceanic ridges, like the mid-Atlantic ridge, that magma is kind of rising up, thinning out the crust, and these plates are kind of pushed up here and are, kind of come down a little bit before they go flat. So because at the spreading center, magma is pushing those ridges up, maybe gravity is kind of pulling down a little bit on those, almost acting like a slide. So gravity is kind of pulling down, saying, hey, no, come on down, helping to facilitate plate movement. So here's slab pull. All right, the part that's being subducted, kind of as it continues downward, is pulling and helping to aid in pull down the plate above it. Again, like imagine, someone is on the cliff and holding on to someone else who's off the side, and they're just kind of slowly both falling over until eventually that person that's on the cliff gets pulled down the side of the mountain or whatever. So that's slab pull. And then ridge push, again, as magma rises up in these spreading centers, it kind of pushes up. That's why it's a ridge. These areas get pushed up a little bit to form these spreading centers, these long mountain chains. That's where the push-up comes from, because that magma is pushing it up. Well, by even slightly pushing it up, right? Maybe that's by pushing it up, you start to slide it down. So let's see. For instance, I don't know. I just grabbed this. I don't even know if this will work, right? So let's say this is a spreading center. Here's a mid-Atlantic ridge or mid-oceanic ridge, right? I'm going to push up on this area, and let's see what happens to the overlying plate. I don't know if that works, but I mean, kind of makes sense to me. Yeah, let's try it again. So, all right, imagine this is duplicated. The divergent boundaries here. There's this here and this on this side. Again, this gets pushed up. Gravity does its thing, pulls it down. I don't know. So anyway, there might be multiple things going on, not just the mantle convection that's pulling on the overlying lithosphere, but also maybe slab pull and ridge push also kind of aiding in the movement. Okay, that's it for this section. So when we come back, one more. I think we can get this done in one more video, and we'll talk about the impacts of plate tectonics on Earth, not just geologically. See you back here in just a second.